So what we're looking at today, this is the last section. And what this is, it's problem solving strategies. And this might seem like a strange thing to cover now. But what we've found in the past is that this section is actually fairly sophisticated. And in some ways, it helps to have a little bit of experience in mathematics before jumping into this section. I know, again, it sounds like, oh gosh, this would be a great thing to have before jumping into some of these other problems in the later sections. But really, this one, what you're going to find, this one's more about creative solutions in some ways, as opposed to, like, for example, there's certain formulas you use in a certain situation. A lot of our problems have followed that kind of a thing. This is totally different. This is oftentimes going to be where we're coming up with creative solutions. And what it's based on is what we call Polya's. Polya's four-step problem solving strategy. And what it is, it's in a way you're trying to help, I guess you could say, inspire solutions. In other words, sometimes if you think about something, you just can't think through it. Like, how do you solve this? How would you approach this? But then when you write it down, you're able to see through it. You can see what approach to this problem. And sometimes it's writing things down, like a list of what's being asked, what we know, what we don't know. It could be things like drawing a picture. Sometimes just drawing a picture helps. I know I had an instructor once, a professor actually, who said this, that you don't want to try to do math in your head. You want to try to do it on paper. And that's why I always emphasize writing things down, because it's easy to get things mixed up in our heads. So let's just kind of go through the steps of this strategy. So the first step is understand the problem.
I'm sorry, I don't know if the picture froze.
Oh, I can wait.
Okay, I'm just double checking. Because I can't see did you write something?
I did. It says understand the problem. It's step one, or number one. Is it still frozen?
It looks like it's still frozen.
Try logging in and logging out. I'll wait. I'll certainly wait.
Okay, then I will be right back. Yeah, I can see.
Awesome. Well, this is step one. It's understanding the problem. And a lot of this, in other courses, they have different ways of doing this. And they'll mention some ways you can do this in this class or in this strategy. For example, they'll say, can you restate the problem in your own words? Now, another thing that can help is, can you determine what is known about these types of problems? So some problems tend to be formulaic in the sense that, well, I want to be careful. That could be a broad description, but some problems you solve with a known formula. And so you can use that formula to solve this particular type of problem. But depending on the problem, is it like a trigonometry type problem where we're trying to use an angle and one known length to find a missing length? Or is it one of the interest problems where you're going to use one of the interest formulas? So what do you know about this type of problem? And that can help give you an idea of what formula to use, or if you needed to come up with a formula on your own, should you draw a picture to come up with that formula? Those kinds of things. Another thing is there missing information? And this is information that you might need to solve the problem. Think of an example that we've run into in our class. You might, for example, let's see, you might need to calculate, for example, the total interest earned. Like, let's say you want to try to figure out, well, actually, we want to try to figure out how much interest is earned over the life of a loan. So to do that, there are certain, in those types of problems, they'll give you information, but they won't actually give you the numbers per se to come up with that total interest earned. You have to do some other things along the way. And it's the other things along the way that could be quote unquote missing information that you've got to come up with on your own. And then sometimes missing information could be something like looking something up. There's something that this question requires you to look up. So you might need like the tangent of an angle or something. So you could look that up in a chart, or you could look it up on your calculator. So there's sometimes pieces that you need, and that's all right. Just kind of mention what am I missing? You write that down and you're all set, or that can help. Another thing, and this sometimes happens, and I think I have seen this happen in a couple of our homework questions. Is there extraneous information? And this is stuff, sometimes they call it red herrings. It's information that you don't necessarily need. They'll mention, for example, something that there's some kind of event that happens in a certain year. In the year, like let's say it's 2004. Well, you don't actually need the number 2004, say, for whatever calculation you're doing, but it is a number that shows up in a math problem, and you might be tempted to say, well, I got to use this number for something. But actually, no, you might not need to do that at all. And that could be just, it's extraneous. You don't really need it. It's just a distraction. Finally, what is the goal? And sometimes knowing the goal, you can use this to work backwards to figure out, well, if I need to get this figured out, to figure that out, I need to figure these other things out. It's kind of like the same question, is there missing information in some ways? If you know the goal, first off, it tells you what you're solving for, but you can also use this to figure out what information you're missing if you're working backwards. Now, another thing that comes up, and this is something that I think really can help. It's a way of figuring out, do we understand this problem? And this actually comes from like college algebra courses. But it also comes up in Math 097. So it seems to be a pretty powerful thing, and it's going to be this. Can we list the knowns? And can we list the unknowns? And that can be a good way of helping us understand what's going on in the problem. Can we list what is known, and can we list what is unknown? And that can help. That's a good place to start, and then to ask some of these other questions as well, to kind of see, okay, so this is unknown. Which of the unknowns? Some of these unknowns could be missing information we need to look for. It could be the thing that our goal that we're actually solving for. What is known? We can look at the knowns and say what information is necessary, what isn't, what's extraneous, these kinds of things. And it's just it could be a good starting point to try to understand the problem. Now, once we have a good sense of what's going on with this problem, what is it asking, what's our goal, what do we need to know in order to get to that goal? The second thing is to devise a plan. And oftentimes this is a good way of trying to come up with a way of helping solve well, of course it's helping solve the problem, but this in some ways gives you an angle of attack, is the best way I would recommend it. And they also recommend listing the knowns. I also recommend unknowns, but list what is known. So this is sort of like your first plan of attack. How are you going to try to deal with this? So they're mentioning knowns and unknowns also. Again, in Math 097, we use that as part of the understanding part. And I think it can help. I might put that in step 1 instead of step 2, but well, fair enough. Now here's a big one. Draw a diagram. In drawings can actually reveal strategies for solving problems in ways that we don't know. Like we might be surprised how an answer pops out. There's one in particular I'll go over where you can draw a diagram. It's like, oh yeah, okay, that's kind of a neat trick. So the thing we can do is we can make an organized list of all possibilities. Sometimes a diagram is actually kind of a thin line between a diagram and things like lists or charts and things like that. They can both give you kind of a picture or a sense of what's going on. And that gets us here, make a table or chart. And the same thing, it can help out seeing what's going on. And there's a great way you can do this. There's a problem with true false questions where we'll use 2 strategies instead of 1. We'll use solving a smaller problem and then using a table or chart to kind of get an idea of what the solution could be. Work backwards. So sometimes what will happen, there's a problem where, how does this go? There's a thief. They steal diamonds and they're trying to escape. And as they're escaping the king's palace, they keep encountering guards. So every guard they encounter, they have to give half of the diamonds to the guard. And as they keep going, so if they have 20 diamonds and they meet the first guard, they have to give that guard 10. If they meet the second guard, they got to give that guard now 5, splitting the 10 remaining in half. Well, what will happen with this type of problem is they'll say the thief escapes with 1 diamond. If there are 12 guards that the thief had to go through, how many diamonds did the thief steal originally? And that's a good problem for the working backwards, because you have the end result and they're asking about how did this whole process start? And so you start with that end result and you work backwards till you get to the how it all started. So that's an example of working backwards. Now, a really good one, I really like this one. Try to solve a simpler problem. And I think this one goes hand in hand with the next one. Look for a pattern. And the reason I think they work together is you can look for a pattern in a smaller version of the problem you're working on. And if it appears that that pattern should always be there, regardless of the size of the problem, you just apply this pattern to the bigger problem. So basically you use a simpler problem, come up with like a formula or a pattern, and then use that pattern or formula in the bigger problem, and then that'll help you solve. Another one. Try to write an equation. And you might have to define each variable. So a lot of this has to do with like mathematical language, like y is directly proportional to x. And there's an equation that goes with that statement that says y equals a constant times x. And or y is inversely proportional to x. That means y equals a constant divided by x. So there are certain things that if you interpret them, you're going to come up with an equation or a balancing of quantities. Now this one might be a little, I don't want to say last resort, but close to it, but you could try. Now this actually, especially if you get into mathematics where, well, modeling in mathematics, you could use this a lot. If you're doing mathematical modeling, trying to come up with an equation that represents a certain natural phenomenon, you can do this sort of thing either in the natural world using data or using computer simulations. But like if you're flipping a coin, if you're not sure about this whole, there should be equal amount of heads as tails, provided the coins are balanced. Well, you can try to figure this out. Or if you have, say, coins that are not equally balanced on both sides, what you can do in that case is you can do an experiment. If you don't mind, I'm going to mute your mic. That's okay.
That's fine.
All right. So you could take like some biased coins and flip them and see what the ratio of heads and tails are. I mean, that could tell you something. And then finally, You can guess and check. So with guess and check, you could argue that you can take an educated guess, and you can whittle down possible solutions and then see which one works. So there's different times. You could use this to kind of check a pattern, see if the pattern is working, and then apply that pattern to a bigger problem. Or sometimes, shoot, I mean, given the options to choose from, you can guess and check. You'd have to say what's called a Boolean kind of solution, where the answer is either true or false, or 1 or 0. And then you could say, all right, well, I've only got 2 possible solutions. I can test this one, see if it works, and then test the other one and see what happens. So there's different ways of going about that. Finally, in the last step, oh, I'm sorry, no, we're not quite to the last, step 3. We carry out the plan. So these are things that, this came up a bit in chapter 11, but the idea is that you want to work carefully. You want to work carefully. That's why I'd try to go through all the different steps there, as tedious as that could be. It's just good accounting. You want to record accurately your attempts. And this can be important because you don't want to reinvent the wheel necessarily. It's really easy to do something and okay, this attempt doesn't work, so you do some other approaches and you accidentally do the same one over again from the beginning. So this kind of keeps you from reinventing the wheel. Also, maybe one of those other attempts really was the correct one. There's maybe just a calculation error. So you can go back and say, look, my intuition tells me that's the way this is supposed to be done, but it didn't work. You checked what you did and you found out, I forgot a minus sign. It's always those minus signs. Those things always get me. Anyway, so watch out for those kinds of things. And then keep an open mind. You may have to modify existing plans. So you could have to go back to step 2 and say, you know, working backwards really didn't seem to help. Maybe I should draw a picture just to see what's going on. So that might be something that comes up. So that's the idea of carrying out the plan. Work carefully, keep an accurate record of your attempts, and be open to the fact that maybe one of these plans is just not working. Got to try something else. For the last step, you can review the solution. So certain things you want to take a look at when you're looking at your solution. Is it consistent with the facts? of the problem. Now, most math problems, you're going to be dealing with some kind of facts, um, usually based in some kind of nature, but who knows, maybe you have sort of a different kind of math problem that might use an alternative universe, I suppose, or an alternative physics. Who knows here? But the whatever those facts are, you want to make sure your solution's consistent with them, that you're not contradicting one of the facts. That's something you do want to check. And that would be a clue that something went wrong. Interpret, and this is kind of the same thing, I think. Interpret the solution in context of the problem. So it's another way of sort of asking, in the context of this problem, what does this solution mean? You could say, does the solution make sense? Is it contradicting facts? Is it what you're really looking for? Is this, when you did your calculation, what popped out when you got your final units, whether they were meters or feet or something like this, degrees, is that what you were looking for? I mean, if you're talking about temperatures and it looks like you're looking for a temperature as a solution, and you get feet as an answer, you might want to take a look again. Something might have gone awry. And then finally, let's see, are there generalizations of the solution that apply to other problems? Are there generalizations of the solution that could apply to other problems? This you could use in a lot of different ways. For one thing, when we get to the part about solving a simpler problem, that's kind of what we do. We solve a little problem that shouldn't be too difficult to solve, hopefully, or at least easier to solve than the one that we're challenged with. And then we generalize it to a bigger problem. So we do use this. You could also use this as sort of saying, I'm going to keep this solution off to the side. I might encounter a problem like this later on the homework, something similar, and then use the same approach because it worked, at least it worked this time. Also, it's a way of checking your solution too. You can say, well, let me put this in the context of other solutions for this type of problem. Again, does the solution make sense? Maybe we have a hard time interpreting the solution in the context of the problem we're working with, but maybe the kind of solution we're getting, the method we're using, that really wouldn't work with other problems. Maybe we should think about this and make sure that what we're doing is actually solving the problem. So that's the strategy. Now, to be honest, a lot of these problems, I think they take some creative thought, and we'll play around with some of these. Let me pick one out here. Take a look. So let's say this. 8 people greet each other and by shaking hands with one another. So how many handshakes are there in total? So this is one of those things, again, we want to try to understand what's going on. And there's some little subtleties that, to be fair, could be just cultural. This could actually be one of these problems that it might depend on context. I'll explain what I mean. So what do we know? Let's take a look at what we know. I'm a big fan of the known and unknown. Well, there's 8 people. Now, what we're going to assume is this. They greet, well, this isn't assumed, this is what they tell us the problem. They greet by shaking hands. But here's an assumption we're going to make. They greet each other only once. Now, I guess it depends on how you define the word greet, or maybe there's maybe different types of greetings that may be slightly more personalized or personal as you go throughout the evening, but we're going to assume that you greet a person once, you do this by shaking hands, and then we don't really consider it a greeting anymore with all the other following interactions. But this is going to be a big assumption that's not mentioned necessarily in the problem. We're going to assume that they greet each other only once. So that's what we know. 8 people, they greet by shaking hands, they greet each other only once. Well, what's unknown? Well, with this, let's use kind of the mixture of what is also the goal. What are we trying to achieve here? So we'll kind of do 2 and 1. It's the total number of handshakes. Total handshakes. That's the goal. So that would be one way of applying step 1. So we try to get a picture of what's going on. We have 8 people, say they're at a party, they're going to greet each other one time. And we want to know how many handshakes actually occur at this party. And it's not handshakes for, say, each person, but how many in total? So this might seem kind of strange, but for step 2, I'm going to draw a picture. Now I say strange because it might not seem like the first thing to come up with, but a lot of these things, again, the way you come up with solutions, well, it's going to be different, say, than somebody else. So give it a try. So one of the key things is this. we have 1, 2, 3, 4, 5, 6, 7, 8 people. So let's say we have 1, there's person 2, there's 3, there's 4, there's 5, there's 6, there's 7, there's 8. So person 1, they're going to shake hands with everybody. Social person. So there's 1, 2, 3, 4, 5, 6, 7. So person 1, there's 7 handshakes right there. Now let's take a look at person 2. They're going to shake everyone's hand. Now they've already shaken hands with person 1. So they don't need to shake hands with person 1. They've already met person 1. Person 2 only needs to meet people they haven't met yet. So there's person 3, there's 4, there's 5, there's 6, there's 7, there's person 8. So we have 7 handshakes, and then for person 2 to finish meeting everybody, they need to make 1, 2, 3, 4, 5, 6 more handshakes. So person 2 adds 6 more that are new. Let's see. Getting another pen here, pardon me. All right. Now, person 3 needs to meet everybody. Now, they've already met person 2. They've already met person 1. So they still need to meet and shake hands with person 4, person 5. We'll do this. Person 6, person 7, person 8. And let's see, did there anyone they didn't meet? Nope, that's it. Now there's another assumption here is you don't greet yourself. We sort of assume you know you. So you don't have to greet yourself. Now person 4, they've met person 3, person 2, and person 1, but they still need to meet person 5. Ooh, keep drawing to 5. Person 5, person 6, person 7, person 8. So you can kind of see a pattern coming out of this picture. And again, with these, you're going to use different, you're not limited to one strategy. We've got a picture, we see a pattern, we could probably guess this is 7, 6, 5, 4, 3 more, then 2 more, then 1 more. Then by the time you get to person 8, they've met everybody. So let's try this. Let's see. So person 5, they still need to meet person 6. They still need to meet person 7. They still need to meet person 8. And 3 more. Person 6 has met everybody except person 7 and person 8. And then person 7 has met everybody except person 8. So 1 more handshake. And then person 8, they're connected to everybody. There's a line going from person 8 to all the other numbers. So that's just going to be 0. So we could have said, well, there's a pattern 7, 6, 5, 4, 3, 2, 1, 0. Or we can just go through, just double check just to make sure that there's no peculiar behavior in the pattern. But this seems, and this is step 2 and it's step 3, to be honest. We're carrying out the plan. 6, 5, 4, 3, 2, 1, 0. And let's see, it's going to be 13, 18, 22, 25, 28. So we get 28 handshakes. And then taking a look at the problem, I mean, does this make sense? And we can reflect on it a little bit. Does this make sense in the context of the problem? And it's like, well, person one, there's 7 strangers they've got to meet, so they meet all 7 of those. Person 2 has to meet everybody, but they've already met person 1, so that probably means there's only 6. You can kind of check your math, see if it makes sense. But that's a way of solving this problem. So any questions about that? Now let's take a look at another one. So this is a true-false test. How many ways can you answer a 12-question TF for true-false test? And this is if you answer each question. You don't leave any blank. And you answer true or false. Well, again, we can think of this in terms of, say, knowns and unknowns. Again, I'm just kind of a big fan of that. Again, you might have a different way of doing this. What I do might seem kind of like I wouldn't, like you might think I wouldn't do it that way, but you know, it works for different approaches, work for different people. I tend to be a picture person, I also like listen charts. And those are the kind of things I kind of lean to. You might have things that you lean towards, go with those, try them out, see if they work. So what do we know? Well, it's a true-false test. So there's basically 2 possible answers or 2 choices. There's no blanks. So you're going to put true, false, one or the other for each question. And there's 12 questions. So what's unknown? Well, it's the number of possible outcomes for a single 12-question true-false test. Or put another way, it's the number of ways or the number of answered tests, really. An answered test, a fully answered test is 1 outcome. And it's the number of those outcomes that we're looking for. And you could break that down a little bit too, to help kind of understand what are we looking for. So each fully answered test is 1 outcome. So each fully answered test is 1 outcome. So we want to figure out how many different ways can we fully answer these tests. Now, this could be something that you might be tempted to try to do this, say, on your own. Like, let's say we have a test, we'll do step 2. We'll try to come up with a strategy. So we could say the first question we answer true, true, true. We can just do true all the way down. Let's see if I have enough room here. Here, let me do this. We'll do it horizontally. Have more room. Three. Yeah, we got 12. So that's a possible outcome. You could do that. You could do this. We could maybe do this. And if you're starting to get a sense this could get really tedious really fast, you're right, it will. In fact, this could get to be pretty overwhelming. There's another way of doing this. And this is where we can search for a small pattern. Let's solve simpler problems. Let's not go for the full 12 question test. Let's try a simpler pattern. And then step 3, we'll go through with it. So let's say we have a 1-question test. Tests like this. There's a question 1. And you can choose true or false. And we go true. And then there's another version of the 1-question test we could do, where we could go false. So how many versions are there of a 1-question test? Well, there's only 2. Now, what does that tell us? It doesn't tell me too much, to be honest. So we'll just put this off to the side. 1 question, 2 versions. You either go with true or you can go with false. Now let's bump it up. Let's say we have a 2-question test. Well, let's see, we could go true, true. We could go false, false. We could go true and false. And we could go false, true, or true, false. Oh yeah, false, true. So how many versions of this test are there? Well, there's 4. So when there's 2 questions, there's 4 versions. I don't know if I see a pattern just yet, but let's try with 3. Where does 3 get us? So we could do true, true, true. False, false, false. Let's see, we could go true, false, false. No, false, true, true. Let's see, what else could we do? We could do true, true, and false. We could do false, false, and true. I'll admit, I'm kind of doing this somewhat randomly. There's a better way to go about this, more systematic way to go about it. I'm trying to spot this. Let's see, we could do a false, a true, and a false. We haven't done that yet. And let's see, I don't think we've done. Haven't done a true, false, and true. Are there any combinations I'm missing? So you have 3 trues. And if we have 2 trues, we can have the bottom one false, the top one false, and the middle one false. We could have 1 true with the bottom 2 false, the bottom top or the top false, and then top and bottom false. Or you can say the top is true, the middle is true, and the bottom is true. And then finally, there's none that are true. That seems to cover everything. So how many outcomes do we have? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 outcomes when we have 3 questions. Now, at this point, we might begin to see a pattern. Get from here to here, times 2. Get from here to here, times 2 again. So what we could do a 4 if we wanted to. If we did 4 questions, what we actually are going to get are 16 solutions or 16 outcomes. So what's going on is that every time we increase by 1 question, we double the number of outcomes. So what this says is this. 2, when we have 1 question, is equal to 2 to the 1. When we have 2 questions, there are 4 outcomes, which is 2 squared. When there are 3 questions, we have 8 outcomes, which is 2 to the 3. So here's a pattern that we could be looking at. If n is the number of questions, and here we're going to be writing an equation. So we'll say outcomes, let's say outcomes m, that's equal to 2 to the n. Wait.
Your video went off.
Yeah, it should be. Let me see. There it goes. All right, there we go. So the number of outcomes m is equal to 2 to the power, that's the number of questions on that test. And so if we have 12 questions.
I'll be right back because my screen froze, so I'm going to try to see if I can fix it.
Okay, no problem. I'll wait. I'll wait.
Be right. I came back.
All right. So now that we have this formula, if we have 12 questions on the test, the number of outcomes will be 2 to the 12. And let's see, what's going to be 2 to the 12? $4,096. So there are 4,096 different ways you can fully answer a 12-question true-false test. And if you tried to list out all the possible 12-question true-false tests, you're going to be here for a while. So solving that simpler problem can really help. Questions about that? Let's take a look at another one. So let's say we have this, 2 ladders. Placed end to end. Combined height is 31.5 feet. One ladder is 31. Ooh, go back. 6.5 feet shorter than the other. find the height of the ladders. So 2 ladders are placed end to end. The combined height is 31.5. One ladder is 6.5 feet shorter than the other. Find the heights of the ladders. So what we can do, again, we can think of this in terms of knowns and unknowns. And again, this is just the way I do things. You can do it a different way. Now, what do we know? Well, there's 2 ladders. And 2 and total heights. (36 or 31.5 feet). We also know one ladder is 6.5 feet shorter than the other. So we know one ladder is 6.5 feet shorter than the other. So what is unknown? Now I'll get in an argument with people over this. I know this comes up in Math 097, but what they will say is the heights of the ladders. But I'm going to argue there's one ladder's height that's more mysterious than the other. The one ladder is 6.5 feet shorter. But there's this other ladder we know nothing about. This other ladder is a total mystery. Because once we know the height of this ladder, all we got to do is subtract 6.5. We'll get the height of the one ladder. So we actually know something about the one ladder. It's 6.5 feet shorter than the other. But the other ladder, other than knowing it exists, I don't know anything specific about it. That's the big unknown. Well, you could say if we add its height to this height, we get 31.5 feet. Okay, fair enough. We do know that. But we know much more. We know more about the one ladder than the other ladder. So let's take a look at this. Let's try to come up with a strategy. And if I'm erasing too fast, please let me know. So I'm going to try drawing a picture. Let's say we set these ladders on the ground. Now we know one is shorter than the other. The one ladder. And then there's the other ladder, which is taller. Now, we don't know what the other ladder is. Let's say we give it a height. Let's draw this out. Sometimes giving it an unknown, a variable label helps. So let's say this other ladder has some mysterious height h. Don't know what h is, but we do know it's a number. And since it's a number, we can give it a variable identity. Now, we know that the one ladder, though, it's whatever this other ladder is, minus 6.5. So if we say this other ladder has a height of h, then the one ladder has a height of h minus 6.5. And this is also step 3. We're going to do these two together. Finally, what other information can we put into this picture? Well, we know the total height of these ladders is 31.5 feet. So put another way, the height of the one plus the height of the other equals 31.5. Now we substitute. Well, what's the height of the one ladder? H minus 6.5 plus the height of the other ladder, which is h. We'll gather like terms. We'll get 2h minus 6.5 equals 31.5. Now we can solve this for h. That'll give us the height of the other ladder. And once we know the height of the other ladder, subtract 6.5 from that, and we'll get the height of the one ladder. So let's solve for h. We'll add 6.5 to both sides. It's going to be 38. Divide both sides by 2. And let's see, it's going to give us 19. So h is going to be 19. So that gives us the other ladder, h. But to find the one ladder, we got to subtract 6.5. So we take h minus 6.5, which is 19 minus 6.5. It's going to be 13, 12.5. And so those are the two heights of the ladders. 19 for the other and 12.5 for the one. Now we could check these. This is sort of our step 4 here. Let's see if these make sense in the context of the problem.
Okay, I'll be right back because my screen froze. Okay.
No problem. All right.
Okay.
Awesome. So to check this, we want to think about the context of the problem. So you have the one plus the other. That should be 31.5. or the 12.5 plus the 19, does this equal 31.5? And if we add them up, we can double check that real quick. Sure enough, they do. So that's one way of checking the problem. Now, a lot of times when you're checking these problems, procedure is something that you can get a problem that makes sense or an answer that makes sense, but it actually isn't the right answer. And that's kind of hard to check. So what that says is that you've come up with a procedure that works, but it still gives you a wrong answer. This is the correct answer. We're okay here, but it's not wild enough to where you would notice it. Like it doesn't, like when you try to check within the context, you won't have something say like this, be a little more vague, and that's sometimes that's kind of hard to deal with. But, you do the best you can. But that's it for today. Now we're not done with this section. That's kind of the part one of this section. We're going to jump into some other types of problems that come up in this section. There's some number problems in here, that, like sums of natural numbers. We're going to take a look at that. So this is part one. We'll do part two on Thursday. Other than that, unless you have any questions, that's it. And have a wonderful afternoon.